Next, we're going to talk about the trend also for some of the atomic properties. So you can see in here we have atomic radius, we have electron affinity, we have ionization energies, and also electronegativity. We will see how the trends for these four properties throughout the periodic table of elements. There are four parameters that we are going to talk about. The first one is the atomic radius. The radius is measured from the core to the outermost electron. So this is the radius. Okay? So right now you are seeing the trend for atomic radius, which is plural for radius. Now in this case you can see that going down the periods from period 1 to period 6, the radius or the size of the atom increases. And this is due to the fact that as you go down the period in the periodic table, you actually add additional shell into the atom. So in this case, the first period has one shell, and the second period has 2 shells, 3 shells, and so on. And as you add more shell, of course, the atom is going to get bigger. On the other hand, going from the left side to the right side in the periodic table, the size actually becomes the size of the atom gets smaller. Across the period, they have the same number of shell, but you have more protons in the nucleus as you go across the groups. And due to the presence of more protons, the electrons will be attracted more towards the core, and therefore the size or the radius will become smaller across the period. So the trend again goes larger to the bottom and larger also to the left side. Okay. Now, if we to compare an atom with their respective ions, for instance, sodium atom with the sodium ion, we know that when the sodium becomes an ion like this, it means that it loses one electron. And if you write down the configuration for this ion, you will see that you're actually losing a shell from 3s. Now it's gone, and then the valence electron or the outermost electron is now in 2p. Now this loss of a shell, of course, results in the radius of the atom being bigger than the radius of the ion. On the other hand, if we work with atom like Cl and compare them with Cl minus, Cl minus receives one extra electron. The upcoming extra electron causes repulsion with the existing electron in the Cl atom. Therefore, in this case, due to such repulsion, the radius of the Cl atom will actually be smaller than the radius of the Cl ion. So it goes for cation, normally the radius will get smaller than the atom, while for anion, the radius will get bigger compared to the atom. The second one is what we call the ionization energy. Ionization energy is the amount of energy needed to be able to release one electron in gas phase. So say we have sodium in gas phase. We want to release one electron, and this, we call it the first ionization energy. Yeah, so we write down 1 in here. we can write down the electron configuration for sodium. Sodium is 11, so it's 1s2, 2s2, 2p6, and 3s1. So we know that sodium is in the third period, in the period 3, in the periodic table of elements, and it belongs to the group 1, yeah, because you see the biggest shell is 3 and it only has 1 electron. Now, if we want to make sodium plus, then the configuration will become 1s2, 2s2, 2p6. Yeah, the electron will be released from the outermost shell. The problem arises when we want to make sodium 2 plus. To get sodium 2 plus, we need the second reaction, and now you can see that now we have sodium plus instead of sodium. And from here, we have the second reaction to form sodium 2 plus gas plus electron. And this is the second ionization energy. So this is the first, and this is the second. Okay? Practically in nature, we cannot observe this process occurring. Why is that? Because you can see if you want to go from sodium plus to sodium 2 plus, this will take so much energy. If you want to go from here to there, because you can see now for sodium 2 plus, the electron configuration is 1s2, 2s2, and 2p5, meaning that you are now removing 1 electron from a full orbital, from a fully filled orbital. It is very hard to remove 1 electron, because as we discussed before, that half filled and fully filled orbitals, they are very stable and they like to stay stable. So if this is fully filled like this, it will be very difficult to be able to take 1 electron into an unstable system like this. That is why the sodium ion that we observe in nature is Na plus and not Na2 plus. The same goes for magnesium. Magnesium is 12 in the atomic number, so it's 1s2, 2s2, 2p6, and 3s2. It's just next to the sodium. Yeah. For the first ionization energy, we go from magnesium gas, always gas, magnesium plus gas plus electron. This is the first ionization energy, and this is okay. You can have magnesium plus, because then you will end up with this one. Yeah. Now, you can still go to the next step to obtain magnesium 2 plus, EI2, because even magnesium 2 plus still results in a stable electron configuration. The problem arises when you want to go from here to magnesium 3 plus, because now you have to pull the electron from the fully filled stable configuration into 2p5, and this is a big no. So for Mg2 plus in gas to become Mg3 plus in gas plus electron, which corresponds to the AI3, the AI3 will be very, very large in comparison to AI2 and also AI1. Therefore, the magnesium that we observe in nature is magnesium 2 plus. As you can see, it has the most stable electron configuration. This is the same with the sodium, where we have sodium plus. And in this case, for sodium, the Ai2 is the one that is really large in comparison to Ai1. Since both sodium plus and Mg2 plus, they both have this electron configuration, we call them isoelectronic because they have the same number of electrons. The trend for ionization energy is the exact opposite of the radius. So down the periods, it becomes smaller or it decreases. And also to this side, from right to left, it also decreases. Consequently, we can say that it is much more difficult to ionize the non-metal in comparison to the metals, because the bigger value of the ionization energy indicates that it needs more energy to be able to release electrons in comparison to the smaller ionization energy for metallic elements. Now we're looking at the successive ionization energies. Now it's here symbolized as I. I before used the symbol of EI, which is energy of ionization, but in this case it's I. It's the same. It means the same thing, which is the energy required to be able to take out or release one electron per step. And for the first ionization energy, you can see for sodium, it is way smaller. It's 10 times smaller almost in comparison to the second ionization energy. While for magnesium, you can see that the first and the second ionization energy, they don't differ very much. However, when you get to the third ionization energy, then this one becomes 10 times also more or less in comparison to the first ionization energy. The ionization energy also has the same trend. So it is higher for group 3 at the fourth ionization energy, because in this case you are trying to release an electron from an already stable ion, which is for Al. That's gonna be Al3 plus. Yeah, Al3 plus is the most stable cation of Al or aluminum. To be able to release one more electron to result in Al4 plus electron, this is going to require a huge amount of energy. That's why this is the most stable form. Just don't forget that everything they occur in the gas phases. Okay. Now on to the third parameter, that is the electronegativity. Electronegativity represents the tendency of an element towards electrons. And across the periodic table, it goes from the left side to the right side. It becomes higher. And across the periods, it goes from the bottom part to the upper part, or the top part, to become higher. Yeah. So the highest electronegativity belongs to the fluorine atom, which sits at this corner. The closer an atom to F, the higher the electronegativity of that said atom. The concept of electronegativity relates to the polarity of a bond. When we have a huge difference, we will end up with an ionic bond, typically in metal pairing with non-metal. In the case where we have both nonmetals, but still we have a difference between the electronegativity between X and Y, we will get what we call as the polar covalent bond. In this case, they share an electron, or they share, to be exact, a pair of electrons. However, the electrons will actually have tendency to be attracted more towards the one with higher electronegativity. This is the symbol for it. And it will be a bit further away from the other atom that is partially positive due to lower electronegativity. And this one has the higher electronegativity. Only when we have another example, for instance, C and D, if C and D not result in any difference in electronegativity, so they both have the same electronegativity. The classic example, of course, the same atoms making a molecule, for instance, in F, like this, Cl. We call this the diatomic system because we have only two atoms, 1 and 2, 1 and 2. And since they both are the same, so FF, Cl, there is no difference in electronegativity in F2, and of course there's also no difference in electronegativity in Cl2. Therefore, these two, we call them non-polar, because there is no polarity, there is no separation of charge like this, either partially positive or partially negative. We don't have this because electrons are being attracted equally to each side. And finally is the electron affinity. The electron affinity is the energy that is involved in the process of receiving an electron. For instance, we have Cl in gas phase as usual. Now it receives an electron, and now we will result in Cl minus in gas phase. The energy correlates to this process. We call them EA. I will write it down like this. Now you are looking at the trend for electron affinity. Just like other parameters, you can also find some kind of trend for this electron affinity parameter. However, in this case, you will find many more exceptions to the trends across rows and down the columns in comparison to the other parameters. Now, in general, you can say that going to the right side, from left to right, the electron affinity becomes more negative. Okay? And as well as going from the bottom up, it also becomes more negative. However, as you can see, mostly it's like that. However, there are several exceptions, for instance, like beryllium right here and nitrogen right here. Now, the way for us to try to understand this is by looking at the electron configuration. If you try to write down the electron configuration for beryllium and for nitrogen, you will almost immediately see that beryllium has a fully filled configuration, while nitrogen has a half-filled configuration. And due to this fully filled or half-filled configurations, they are more stable than the rest of the elements right here, and therefore it will require more energy for it to be able to gain electron. Don't forget, electron affinity has to do with the energy involved during the acceptance of one more electron. And in this case, when something is more stable, then it will require more energy, while the rest is releasing energy. If it's negative, it means that the energy is being released. If it's positive, that means the energy is being used or being demanded by the system. And as you can see in here, mostly for these are the values for the first electron affinity. And as you can see that the values are mostly negative or more or less 0 or bigger than 0 like this. So it's supposed to be positive. While for the second electron affinity, all of them will be positive. So it will require energy to be able to introduce the second extra electron for any atom. Just like the ionization energy, the first electron affinity, or you can also write this down as EA1, it has to do with this reaction, yeah, plus electron. Don't forget, they are always in gas phase. And the second electron affinity, it will receive the second extra electron, so you get 2 minus like this. For EA2, it's mostly positive because it requires energy to be able to introduce an extra electron that actually will be repulsed by existing electrons in this anion. While for EA1, in this table, as you can see, mostly they are negative. However, we have several exceptions like that, especially when the configuration is fully filled or half filled.